So this video of Japanese multiplication has been going around for a little while, and even though I would be really surprised to learn that it had anything to do with actual Japanese people, it's interesting to look at how we can take a multiplication problem and turn it into a counting problem that we can solve visually. And if you think about it, for most people, for most of human history, that would be really useful, because learning your multiplication facts was not super high on your priority list if you were, say, a 14th century European farmer who was trying not to starve to death or die of the plague. But you still had to multiply things once in a while. So it'd be nice to have an algorithm that lets you do it just by counting, kind of as a rule of thumb, even if you didn't understand the actual math. But we can take a look at why it works. First of all, notice that if I wanted to multiply, say, 4 times 2, I could represent 4 with lines or sticks or whatever, and then cross that with 2 more. And if I count up those intersections, there are 8 in there. So what this picture really represents is the multiplication fact, 4 times 2 equals 8. Except I don't have to remember it, it's right there in front of me. When we move this into the context of a larger problem, you can see where it really helps if you don't know your facts. So I'll represent 21 with 2 sticks for the tens and 1 for the ones, and then 13 with 1 and then 3. You'll notice that this really isn't much different from the way we write things in numerals. That 2 and 21, for example, isn't really a 2, it's a 20. And those 2 lines on the left aren't really 2 lines, they're 2 lines of 10 each. We can color code them and make it a little bit simpler to keep track of. So there are the tens and the ones. Well, let's see how this stacks up against our kind of normal multiplication. If I start off on the right with 1 intersecting 1, there are 3 of those intersections, which corresponds to 1 times 3, and I leave it in the ones place. On the left, if I count those 2 intersections, that's really 2 tens and 1 10. So that 2 is not really a 2, it's a 200. 20 times 10. And then in the middle, I have red intersecting green. So up here, that's 2 tens times 3 ones, which gives me 60. And then down here I have 1 10 and 1 1, which gives me just, well, 10. So that's a total of 7 tens. And you can see that that matches up with our multiplication on the right. Some of you may recognize that as the partial products algorithm you probably learned in school at some point. If we want a little bit trickier problem, one that requires regrouping, we can try 123 times 321. There's 3 hundreds, 2 tens, and 1 1. And let's color code them again. Hundreds, tens, ones. Well, if I look out here where my ones intersect my ones, I wind up with 3 intersections. And so I leave that 3 in the ones place. Next up, I have yellow intersecting green, which means I'm getting tens and ones. So out of that, I'm going to get tens. If I count up those intersections, there are 8. So 8 goes in the tens place. On the left, I get 3 intersections, but that's hundreds and hundreds, which gives me 10,000s. So 3 goes in the 10,000s place. Now I have red and yellow, so that's hundreds and tens, which is going to give me thousands. If you count them up, there are 8 of those. And in the middle, I either have red intersecting green, which is ones and hundreds, or I have yellow intersecting yellow, which is tens and tens. Either way, that's the hundreds place. And if you count them up, you wind up with 14 hundreds. Now, just like in regular multiplication, that's a problem. I can't have 14 in the hundreds place, so that really is 1,400. So I take that 1 and I bump it over to the thousands place, and I wind up with 39,483, which happens to be the correct answer. If we want to simplify things a little bit for ourselves, we can take a look ahead of time at where our intersections are going to leave us, and we can write out some placeholder zeros. For example, these are hundreds times hundreds, or 10 squareds times 10 squareds. That multiplication is going to leave me with 4 trailing zeros, because 10 squared times 10 squared gives me 10 to the 4th. So that 3 I get when I count up the intersection tells me I really have 3 10,000s. In the next space over, now I have 10 squareds intersecting with just tens. So again, that's going to give me 3 zeros, because 10 squared times 10 to the 1st is 10 to the 3rd. So when I get those 8 intersections, that tells me I really have 8,000s. If I bring the ones place into the mix, now I either have 10 to the 0 times 10 squared, which is 10 squared, or I have 10 to the 1st times 10 to the 1st, which is 10 squared. Either way, I get 2 trailing zeros in the hundreds place. So when I count up those 14 intersections, that tells me I have 14 groups of 100. Now I have yellow and green, which is my tens place and my ones place, which is going to leave me with one trailing 0, or 10 to the first. There are 8 of those, so I have 8 tens, or 80. And finally, my lonely ones, intersecting ones, I'm going to have no trailing zeros, so those 3 that I get just go at the end. Now when I add them up, I get the same result as I did before, 39,483. Well, let's go back to that first problem. To really appreciate why this might be useful if you don't know your multiplication facts, we have to pretend like we don't know our multiplication facts. And for most of you, that's probably really hard. So a nice trick is to try doing it in a different base. Because if you're like me, you don't know your base 6 multiplication facts, but you can count in base 6. In base 10, when we get up to 9, we put a 0 and we move one place over. So now we're going to try it in base 6, and we're going to get to 5, and then we'll start with a 0 and move 1 over in our place value. So 21 is just 3 3 in base 6. You can kind of verify that 2 10s and 1 1 are the same as 3 6s and 3 1s. And then 13, which is 1 10 and 3 1s, is also 2 6s and 1 1. So now we can draw our picture just like we did before. 3 in the 6s place and 3 in the 1s place, 2 in the 6s place, and 1 in the 1s place. And again, let's color code it to keep track. Now, when I look over here, this is my 6s place intersecting with my 6s place, which in base 6 is just 10, or 1 0. So I'm going to leave myself with 2 trailing zeros, just like before, which is 10 in base 6 squared. So now I count out my intersections, remembering that I'm counting in base 6. So that's 1, 2, 3, 4, 5, 1 0. So I have 1 0 groups of 10 squared. My middle intersection, now I'm bringing the ones place into play. So this is going to leave me with 1 trailing 0, or 10 to the first in base 6. And I count those again, remembering that I have to roll over at 5. So I have 1, 2, 3, 4, 5, 1 0, 1 1, 1 2, 1 3. So I have 1 3 groups of, let's say, 10s. My 1s I treat just like my 1s, and I have 3 of those. And when I add those up, you can see that I get 1,133, or really 1133 in base 6, which is true.